Hey, P-Stats, continuing with Chapter 7 notes. If you remember, in our last session, we were talking about the number of pairs of jeans someone buys and the total cost, and we saw that there was this linear relationship, positive association, looks moderate in strength, and we were actually able to calculate the correlation coefficient. We figured out that that was 0.74, and we figured out the linear model or the linear regression equation that modeled the situation. That's y hat equals 54 plus 26x. So this is the equation of the line that best fits our scattered plot. We're going to continue with some of the kind of details of linear regression here. So what we have based on this equation, remember that this equation, this helps us predict values. So what is a predicted value? It's this y hat thing. So if we have this point x comma y, maybe this is the actual point. So like in our example, these points down here, 1, 2, 3, 4, 5, 6, these 6 points, which represent these 6 dots, these are the actual points. Like they actually happened, x comma y. Like we bought 4 jeans and they were $125. We bought 6 jeans, they were $200. A predicted value is when we plug an x into our regression model and we have a y hat that comes out. So we have an actual amount. In this case, we have 6 actual figures. But then we can get predicted amounts by plugging in an x coordinate into our equation. Now, what you'll actually see here, guys, is that when I plug in an x value into our equation, we're not always going to get the same value. So I'll actually show you that right now first. So we'll come back to this residual. So here's our original point, 4, 125. If I want to get the predicted value here, I'm going to take my x, which is 4, plug it into my equation. So if I did like 54 plus 26 times x, which is 4, so that's 104 plus 54, 158. So notice that my predicted amount for 4 jeans is 158, but we actually only bought 4 jeans for $125. So they may be off a little bit for certain points, but that's okay, because at the end of the day, this is the best model that fits all of our data, not just this one. So if I keep going with that, if I did for my equation over here, 54 plus 26 times 6 equals... Alright, so I filled in the table there, and again, all I did was plug in these x values, 4, 6, 7, 7, 8, 13, into our linear regression equation, and we got the predicted values. Now, if we look at our predicted values compared to what they actually were, like when we bought 7 jeans, we bought for 150, our model predicted 236. We bought them for 275 also at one time. We bought 7 pairs of jeans. And again, our model predicted 236. So we can see that they're off by a little bit. And what we call that value that they're off by, we call that a residual. So what a residual is this is your actual value minus your predicted value. Or you can also think of this as like your y value, what actually happened, minus your y hat. And if I did that for these examples here, so like 158 minus 125, the other way around. Actual minus predicted, so 125 minus 158. This is negative 33. And again, 200 minus 210 is negative 10. Keep going with this. If we filled in the rest of the table, here's what we get for our residuals. And if you notice, some of them are positive, these two, and then some of them are negative. So what that means, guys, is here's a little picture. So let's say this red line, that this is our linear regression equation. So let's say this is our regression model. And let's say I had like 3 blue points that were above it, and maybe also let's say we have like 3 blue points that were below it. Having a positive residual, so for example 39 and 113, if you have a positive residual, it means that your actual point was above the linear regression equation. So these are all positive residuals. And what it means for positive residuals is that these values are actually more than the model predicted. So in this case, the model underestimated. And for these values that are below the linear regression model, these have negative residuals. So that would be like this one, this one, this one, and that one. And these negative residuals, you can see that they fall below the linear regression equation. So the actual points were below the model. So in this case, the model overestimates. So these are overestimates, and positive residuals are underestimates. Positive residuals, the points are above our line. Negative residuals, the points are below the line. All right. And how do we know we have the line of best fit? Well, if you remember, I told you guys that our calculator figures out this advanced formula, and they give us this equation, right? And I don't think any of us really question, like, okay, how the heck did they get that equation? Well, what the calculator does is, through a series of calculations and limits, they figure out what line minimizes all the residuals. So the line of best fit is actually a line that minimizes the residuals. So we actually want these distances, the total distance, to be as small as possible. And that, we know, would be a line of best fit. Okay, so continuing on with this line of best fit. So like we said, it's a line that minimizes the sum of the residuals. We're going to skip a lot of questions here, but one thing to really understand with this is that a line of best fit, it should go through the average of all your x coordinates and the average of all your y coordinates. So real quick, if I just drew this scatter plot, and I just drew a line of best fit, you notice that like the line doesn't go through every single point. Maybe it goes through one, maybe it goes through none. That's fine. But if we took all the x coordinates of these 1, 2, 3, 4, 5, 6 points, and we found their average, that's x bar, and we did the same thing for their y, maybe I'll make that point in blue. maybe that point ends up being right here, this blue one. So this isn't a real point. But what we know is that for all linear regression equations, they have to go through the points x bar comma y bar. All right, and we're actually going to see that here in a second. So in our data, what is the typical number of genes purchased? So for this, guys, I'm actually just going to take the average of all my x coordinates. So 4, 6, 7, 7, 8, 13. And that is 7.5. And then what is the typical total purchase cost? Again, I'm just going to take the average of my y coordinates. So if I did 125 plus 200 and so on, divided by 6, we would find that the typical cost is, say, 245.83. All right. So what we know about this is that our equation y hat equals a plus bx, this can be manipulated a little bit. And I say a little bit because we can plug in a point. So this is the equation of our linear regression model. And we can plug in a point x comma y, or x comma y hat, that we know lies on this regression equation. And that's this one. So if I were to just substitute, I'll do this in a different color, we have this. And this is an equation that you'll see on, both of these you'll see on your formula sheet at the end of the year. And all this means, guys, is this is the fact that we have a linear regression model goes through the points x bar, y bar. And again, all x bar and y bar are is the average of all the points. So we'll go ahead and stop there.